Okay, welcome back. But the next talk is going to be something different, and very interesting. From Dr. Masayoshi Kosai, uh, from he's a project researcher at the Research Organization of Information and Systems, Japan. I don't know the AMIDA project, AMIDA project for open science in polar research. Floor is yours.
For introduction. I'm from PDSC OSDWG in Japan, and I talk about AMIDA project for open science for our research. So maybe very current the session. As a background, I introduce our center. Our center, Polar Environment Data Science Center in OSDS Japan. This is from our website. You see, our goal is to promote management use of research data, mainly polar science. Polar science covers diverse sciences such as space science, geoscience, bioscience, or there's also historical science. So we are, by leveraging this situation, we are developing a cross-disciplinary promotion site for research data. It's a concept of AMIDA website. As I thought, we expect it will be a one-stop gateway diverse scientific fields. And we imagine it's like a virtual museum, research data. Here, I call the research data, observation data, or specimens such as animal specimens and so forth. And so researcher gets the data by experiment, work, make it open our rules. Our targets are non-specialized users, such as researchers interested in collaborating with diverse scientific teams, or educators, students. And of course, the specialized researchers are our students. And they will find research data in diverse scientific fields by the website. And we thought it will make the research data more open and promote cross-disciplinary collaboration and research. As a first, I talk about our user interface design. This is catalog view. Our designs are inspired by marketing such as Amazon. There are many hints for promotion of such data. But for example, this catalog view it displays AMIDA contents or data sets at a glance. We use common design, but it consists of thumbnail images and snippets. Snippet is blog title, short description. Research data, we can imagine the contents at a glance. by this page. So users can browse the contents only by browsing the catalog view, and we hope it will make the research data browsing itself exciting. This is the individual dataset page. This is the example of time series data in space science. For space, geospace science, this is the magnetic field, geomagnetic field. Data type being data title is in terms. Use of scientific terminology is nice, and it's descriptive, easy to read. There's also functions. This will experts. One is a data download function. Multiple files are downloadable at once by selecting the period time series data. Both the original format, binary, and converted plain text data are selected. And this is visualized data. It's used to the mainly data plots, but any kind of image can be registered the evidence to this. Again, the display period is selected. And below this, there is a somewhat unique function proposing related datasets to each dataset. We calculate correlation scores with such data. Here is downloadable data. We calculate the correlation score and is to here and any related datasets. And it is also useful to browse the datasets simultaneously to browse at the selected time series data. So the time we select and we can display which data is available at the time. We hope it will induce a cross-disciplinary walk-around experience with datasets. And the calculation of correlations. Now it's only by the correlation scores between the chemical data, but we are developing calculated correlation based on text and image processing. It's necessary and under development, but it will propose related to data sets, other scientific fields by using such as observation location or observation target as a goal. And there's of course the metadata table. Again, the description with plain terms placed here is minimized use of scientific terminology. And there's also a term of individual data defined here. It's very important for data providers to define the term of use. And this is another example, animal specimen data. Very different kind of data from the time series data, but the uniform designs, designs. We use a configuration file each display element, each data set. So keeping the uniform design, but we can display very different type of data by our tools. I show the real website. Japanese and English and Japanese interface is very important for the Japanese people. from top science. And there's a search function here and some major keywords. Once we look here, the dataset page, this is a magnetic field data without the show station. The download function. And available time. There is no numerical data file, but we can use such a kind of data or metadata. We can and meteorite is also one major field for science. Next, I talk about system design. This is system overview. Most important is metadata files. It's made in some standard scheme, like size and space scheme. Another is ISO standards. And also, as I explained, we can download each such data files from our browser. And it's not pressed at the server. But Amida is putting the URLs each data files. So the original research data is managed by remotely pushed. And but there is a recommended format. Why she developed another I will explain data. And for these formats, Amida's advanced functions are right. But also any format is accepted only for file download function. And but as a backend process, so there is a dataset registration function. And there is a research data download function. And as an advanced functions for research data, we will provide correlation score between datasets. And there is also file conversion binary format. Special scientific fields to bring pixel format. And we are also providing future developments such as process. And there's a application. Metadata format. One of the format we use is the space physics archive search and schema. It's managed by Space Consortium. NASA US and website. It's a standard format of space physics. And also solar terrestrial dynamic science. Amida's space science data for solar terrestrial environment science such as magnetic data provided. And another format is geographic information mathematics schema, ISO standard. It's one of the standard formats used by here, for research in Japan. So these standard formats and interoperability platforms. So Amida can use datasets already established datasets in each type of field. So actually, we at the current moment, Amida's one of Amida's main contents came from Yugon. It's a solar terrestrial science database in Japan. And ADS is a standard database like here. And about the data formats, research data files, they are self-describing machine-dependent binary formats to make interoperability platforms. One is CDF is a common data format. It's managed by Goddard Flight Center as a standard format in space science. So Amida's space science contents, such as polar image about atmosphere data, are provided in this form. And another is NetCDF common data form. It's managed by SF data community. Yes. And it's standard format in many fields, but meteorological science. So Amida's meteorological meteorite sample data is also provided this form. There are many applications based on this binary data form. These are binary data, so for the non-specialized users, we provide the conversion function from this binary data to this ASCII plain text form. Current status that Amida is not in public operation yet, but the basic system has been fixed, and we started operation test the website that is in our center. And we will start a public operation after all preparations are finished. It's planned around the end of March. And the future prospect as a one pillar of our next development will be supporting data providers by digital transformation, data curation process. Data curation process the research data API to register database and make it open. And it's a one of the hard work the individual researchers, but it's a very essential open science. So providing the data providers will promote data publication for open science activities. And it will also, by the digital transformation, enhance the quality of database. One attempt to semi-automatic generation of the data by a dedicated application. We will develop such application. And another pillar is advanced proportion research data beyond the Amida's data pattern. One concept is visualization context behind the research data. It means how is the data obtained, or how is the data used, or what is the science behind the data. It will be the context behind the research data. Only by the metadata table, non-specialized user cannot imagine the context of data. So some idea will require from the open science. It will visualize dynamic research activities from the viewpoint research data. And we hope it will support diverse users to create a new demand for such data by themselves. It's already a common approach in the web market, such as Amazon or YouTube. There are images, commercial products, and we can imagine how it can be used for background story product in the website. Ameda's catalog view, thumbnail, and snippet will attempt at this concept, and future development can be done. Key technologies in natural language processing or text mining, image processing. And this is one attempt text mining search data promotion. This is a four-parent network comes data title inside Amida for space science data. And such as the shower station, or magnet meter or radar appears as a node type. Such an attempt to visualize the overview side views of the people such data. So we will put such a visualization and put the result such a visualization on the website to promote the open science. And as a rest, maybe you don't know what is Amida. Amida is came from Japanese name Abidaku. So, and what is Abidaku? And Google translation says Amidakuji is Abidakuji. So there is that, and I found expression in Wikipedia. It's a type of water in Japan. Each participant here and these are each result, and the participant can get the result by transversing the vertical lines. So Amidakuji contains the image most discretely move around between the scientific fields. So we use the Amidakuji and make the website. I mean, just it. That's all.
Very interesting. I have a question. Who installed the instrument and how do you maintain it there in the cycle? Instrument, where is the instrument that you install? The instrument that collecting data.
It's we are just collecting the data from each researcher. So each research, so if a researcher picks the extreme, the data will be keeping open. But the end of there's the end of the time.
So this is from different researchers that open the data, or from the Japanese scientists?
Yes.
So somebody from Japan went there to install the instrument.
Sorry.
The Japanese researcher, is it Antarctica?
Yes, it's mainly for our science. So
Okay.
Antarctica. But
Right.
it's not
Right. Okay. But the people that go to the site to install this equipment, there's a Japanese researcher.
It's not confined, but at the current moment, as I talk, it's a very preliminary stage. Just we are starting to operation. So at the current moment, we need to contact each researcher by ourselves and present data.
Not from your center. The instrument, not from your center.
Not from our center. It's various researchers Japan, but not by ourselves. So in future, we hope that researcher find our website and they will say us, please open our data.
So how do you talk to them to open this kind of data? It's like very specific. So how do you approach them to share this kind of data from their institute?
It's a very simple negotiation by contacting them
Or they just
at the current moment. So I don't know how is the strategy for it, but yeah. But in future, I hope the data register system, our website, so researcher can use the system and somewhat automatically start their data. Yeah, but it's a future development. At the current moment, very simple negotiation by email.
very difficult to listen to the second speaker. That it's really difficult to ask people to open the data. Other group.
So yeah, and actually in the environmental research, make the data open, the already common
In Japan
strategy. Yeah,
or
because we collect kind of data such as the atmosphere and analyze. So almost data are already stored in the open database provided, but our concept is make it open also for more specialized users. So yeah, so I think so the make the data open is already common, especially in the environmental study, such as earth science and space science. So just we are doing how we how we promote the data. Yeah. So actually, as I talked, at the current moment, the main contents of AVIDA, major contents of AVIDA are from the already established database, such as Ugonet or ADS Japan. So it's already open, and we collect and we provide another uh, another promotion scheme in our website. But yeah, and there is also our specialized data, such as animal specimen and meteorite sample data has been not open. There is no open database. So especially for these data, we contacted to the researcher in Japan. By so, yeah.
Very interesting size. Do you provide any climate change data, like the temperatures or wind, sometimes related to the climate change? If we can search the that kind of data, therefore,
But at the current moment, it's very at the at the current moment, our main target is for science. So these data are collected by researchers, for science researchers at the field. The field. Yeah. for the satellite data, there is already a very big database system. So we are not but there is already some climate or atmosphere concentration data. They are provided by some field researcher. Maybe it's not so open. I'm not detail in this field, but I hope it will be valuable research. I think they are already published the NIPR database system in Japan. Yeah, but only the internet.
Yeah, I second. It's a very interesting one. I'm not talking about the financial incentives. Searchers for data that it is okay. Are you giving any incentives to searchers? Certainly incentives, benefits.
Yeah. Yes, it will be a big issue in the open science. Actually, yeah. Issue and at the current moment, I'm focusing developing the system and not thinking about the details for that issue. But yeah, and yeah, maybe there are many kind of incentives. So one will be the foundation, or another will be the environmental research field. We have to collect various kind of data to analyze the data, and it's not an incentive, but one of our plan is to make the data publishing for easy researchers by making some application to make metadata. At the current moment, I'm focusing on help researchers to
Thank you very much. And move on to the next speaker, one of our own, Marcus. So he will give the talk, the context of Australia. That we have more discussion, working tomorrow. And that this is what the problem that we're trying to solve. Because of this open data, you get good data too. It's open, not just like everything. But when you're saying like big data, people sometimes include bad and good data in that big data, and then so that's also one. So, good quality data, open, but trying to do that, but within the context of data. First, try to expand. This is one issue. And Marcus will give a lot because Australia have been doing it, and then they are very successful. You want to do something, then you can just go into the system and then point it out and then keep all the results. The e-research framework for the grant count. Marcus, the floor is yours. You have only 30 minutes because he always talk for 3 hours. So
Try turning it on. That's it. I was actually going to say that at the last APAN meeting, literally as we were leaving Sri Lanka, Jai said, "I'm running this session. You're going to talk." And he beat me up for the next 6 months. So, yeah. I'm not going to talk about a specific project, a specific infrastructure, because what I want to talk about is, in fact, a much larger framework that supports schools globally. And I'll use Australia as an example again, but I just want to talk a bit about the context and the focus on data. So one of the things we've seen over the last, particularly the last 25 or so years, is that research has changed. There was a time where individual researcher of a small lab could tackle major problems, make huge impacts. Nowadays, it's all collaboration. We have bigger and bigger groups. Some of the physical science papers have come up recently. The Higgs boson, about 10 years ago. The list of authors took up more pages than the actual paper. There were over 1,500 authors involved in one experiment. So, when you think about the level of research activities that occurred globally through COVID, that was tens of thousands of researchers working globally, sharing data, moving back and forth very quickly. We're tackling major health issues like cancer. Obviously, climate change is a major challenge as well. In the ICT world now, we're seeing this huge uptake, machine learning, AI, activities and so on. And it is not individuals doing this information. And jokes that in Australia about that, a researcher does not identify as working for an institution. They identify with discipline. They have to look at their business card. Oh, yeah. But they say, no, I'm an astronomer. I work with astronomers all over the world. So the other thing that's changed is that it's become much more data-driven, but not your own. So the problem is that if you want to try and compete globally, like researchers work with data sets, is you don't have enough time during the PhD or during a project to just collect the data you need, work on it, publish, and then move on. Because what you're doing is you're competing with somebody who's looking at 10 data sets together, a whole bunch of different insights in a way that you're not able to focus on research. The other thing is, it's not just your infrastructure, and come back to that point, but there was a time when a single researcher, when they started a new project, they put in a grant application, they say, oh, I want to buy a computer, and they're not running these things. But they basically, that was the only way they thought about infrastructure at the time. So nowadays, they tend to use other research service providers and so on. And it is actually quite a competitive thing. So this becomes very important. When you use the word infrastructure a lot, most people, especially when companies like this, think about the technology. I want to include infrastructure people with skills, people with experience, people who can provide advice. Really. Infrastructure includes the policy framework. If your government has a policy that you can't research and can't collect certain data, stop. You can't work in this space. You need to have the right policies. You need to have the right practices. That's about the culture of research infrastructure and research data and so on. Where somebody once said, culture eats policies for breakfast. It's basically a joke about the fact that what people do, they will keep doing. If you write a policy that says you shouldn't do this anymore, child, that's the wrong way to do things, it's going to keep doing it, right? Because you're used to it. You've worked that way your whole career. Why would you change? It's got to be a benefit. And I like the question earlier about what are the incentives. In Australia, we use the term e-research. Other countries use the word e-science. We used e-research in Australia because the humanities and social sciences thought that e-science was too much about physical sciences. We want to be much more scientific. The Americans called it cyber infrastructure because they didn't want to do cyber. So they just thought about the technology, but they didn't think about it. One question that came up was, who owns that infrastructure? And there's a couple of perspectives on this. One thing I want to focus on is there's different owners of different things. So we started off in a world where all of the research infrastructure was developed bespoke for a particular project. Kazakhstan's about the AMIDA demonstration is about collecting the data, putting it on a server, Facebook, so on. And that's the way the vast majority of research infrastructure is built. Subsequently, the same is that there are certain elements of that infrastructure that generally becoming standardized. So there's a discipline level of infrastructure. And some of that is the people and policies. It's the standards. It's the metadata standards, the file format standards. Every discipline now has standards for the data and the typical tools they use, because everybody developed their own, and there were hundreds of different tools for hundreds of different tools for linguistics. They've all started to consolidate, simplify, streamline, so they become more similar. And then we ended up with a much more common infrastructure underneath. There was a time where every researcher bought it. Don't do that anymore. Have general purpose supercomputers. We have shared networks. That's an obvious one. Very few research groups build their own networks. So we're now getting these different layers of infrastructure. Now I'm drawing them as hard layers. It's actually much more complicated. Some disciplines don't have much of their own object bespoke infrastructure. Some of them have very deep and complex. But common infrastructure is coming up. And one of the things that's interesting is that that is where the commercial is starting. You think about the Amazons of the world, they're starting to have data sets available. I had a discussion with the head of Amazon Scientific years ago. We talked about the fact that in Australia, the National Supercomputing Facility, or facility, is in the top 25 to 30 in the world, usually. And it's a really big high-performance machine. And he said, yeah, it's a great machine. It's huge. Amazon Scientific Computing installs the equivalent of our national facility every 12 hours. Twice a day, they build national facilities in Australian state. And they do it. We can't compete. Now, their compute infrastructure isn't suited to every kind of problem. Anybody here is involved in HPC and budget computing understands that. But that is where the commercial world is starting. We need a lot of additional services. We used to joke about tech under the desk. This is where researchers bought. A lot of this is about the financial pressures. There was a time where you could buy your own super, had it book to yourself. Nowadays, you buy it pretty easy. A lot of researchers are still building custom database systems. Telescopes, not so much anymore. Microscopes, still quite a lot of that going on. Sensor networks, yeah, that's easy to do. Satellites, no, most researchers are not launching these. But there are some. Biggest things that have changed have been things like data storage. And one of the things that really scares me is this, right? That is a 1.5 terabyte micro SD. Look at my finger now. This is just amazing. The first hard disk I ever bought, young lad, was 80 megabytes. Big chunk of metal, it weighed a lot. So, yeah, and you can buy this at most office shops. So the ability to store data has gone dramatic. And there's something that comes with that, which is our ability to generate. When we started doing gene sequencing, our science communities, first time we did the human genome, it took 106 years to do. It cost $100 million. It improved a little bit since then. This was 2000, 20 years ago. The National Institute of Health in the US has actually kept the data on costs to map an entire human genome. Starts off at $100 million back in 2000. Notice it comes down with more. And then we had some major changes. Around 2007, dropped sharply. We started getting these automated gene sequencing. So they basically specialized chips to do the chemistry. They would split things up on the chip, on the fly, and instead of taking 6 years, it would take a few months. Notice the price dropped sharp. It kept going. And then around 2014, there's another big parallelism. It's quite a lot. Chips much smaller. Cells on this chip smaller. We're now at the stage where the genome, to sequence a single genome, is closer to $100 instead of 100 million. It's a factor of a million price performance. 20. That is just an amazing. Does that change things? Absolutely. So when you had a researcher trying to do gene sequence analysis, they'd be lucky during their research. They could sequence one per gene. Nowadays, we can do multiple families, multiple types, different patients. How much data are they generating? We used to sequence somebody who had a disease and try and understand it. Nowadays, we can sequence entire populations. People who have a disease, people who don't have a disease, compare and trust, and work out which particular gene causing the disease. We used to have one sequencer for a country because one of these things was insanely expensive. We're now easily in every single lab on most universities around the world. Now this infrastructure is becoming really, really common. We're starting to see some labs setting up as a service. So they're turning it into common infrastructure and saying, we're going to share this scale. All of this stuff generates huge volumes. And what do we do with that? Well, there's some interesting things that come out. So one of the things that's come out a lot is the unexpected reuse. There was a lovely example published in New Zealand 15 years ago. They looked at traffic data, vehicles on the road. And it turns out if you measure the number of trucks on the road, it correlates pretty much perfectly to current GDP. Which is no surprise, right? The more economic activity you have, the high-end building factories, whatever. So number of trucks should correlate to GDP. When you look at light vehicle traffic, small cars, people going to business, and so on, it actually predicts GDP by about 6 months. So if you have somebody who's studying economics, you're going to start looking at traffic. Because you're going to try and understand what is happening, what's changing, what are the likely implications we're going to come up with GDP. So when people talk about, oh, we've just had an announcement of GDP, I can tell you what the value is 6 months ago. That's an amazing. There was a lovely example of whaling. People used to collect or used to hunt whales in the Southern Ocean, Antarctica, and they kept really good records of every single whale. And like, why would anybody pick that? Why is it interesting? Well, it wasn't interesting to anybody except people hunting whales at the time. Today, it turns out when you catch a whale, you don't catch them where they're catch them on ice. So it turned out when you actually mapped the whale, it showed you where the ice was up. You suddenly had about 200 years worth of ice sheet kept in whaling. Correlating those two until somebody sat down and went. Another good example, the Hubble Space Telescope. So Hubble is an interesting one. I asked the question before about access to data. Hubble is a telescope that's up in space. You bid for time on it to collect data that you're interested in. Now, with most telescopes around the world, you collect the data from the telescope, it's your data. You publish about it, share it, however you see fit, and so on. Hubble, when it was launched, talking back about 1990s, made a really important decision very early on. They said, we're not giving you the data, we're leasing, giving you a license. You have 18 months to publish everything you can about the data you've made. After that, it goes in our public. Anybody else who wants to use that data then has access. What they found is that for every single paper published by a researcher who collected data, There have been another 5 to 6 papers published by other people using the same data, doing different kinds of analysis, looking at different objects in the field, all sorts of different things. So the Space Telescope Science Institute, they run a big data archive, they keep the data, they use it, then it becomes publicly available. And anybody here can log into it. It's completely public. Another one that came up, there's a little bit of an urban myth around it, but it's basically industry where people looked at shopping habits, credit card data information, time of day, all sorts of different things. And this actually came down to supermarkets who looked at the way people products shops. They noticed a distinct peak in the purchase of children's nappies around 6 o'clock in the evening. There was another peak that went alongside it. And what happened was that basically husband's working, gets a call from the wife saying, run out of nappies, get some on the way home. Husband goes, I'll go get some. It's like, supermarket, what else should I? I'm not going to get some. This was so prevalent. This was actually a correlation. And so a lot of supermarkets redesigned their shops. They looked for other correlations, but this was the most obvious. So some of them went one way, some other. Some of them would put nappies in the big buckets. Jason, make it easy, just to remind you, hey, look at the nappy. Other supermarkets went the other way. They put nappies on one side, but fast. So you had to walk through the rest of the shop. You might impulse buy additional things. So they were data mining by linking different things. This unexpected readers comes up and okay. So we have lots and lots of valuable data. Many different sources, research, collect data, it's all going up. Some people have talked about they're now talking about peak storage. The problem is our ability to generate data is going faster than our ability to build. I don't know whether that's true. The main thing is actually this last point. IBM, about 15 years ago, published a paper that said we generate about 2.5 exabytes of data per day. I think it's Tera, Peta, Data, X. Every one of those is a factor of that. That's per day. If we talk about all of the data in the world today, 90% of it is collected in the last 2 years. Over all of recorded, 90% of the data is so if we're going to try and fix things and improve the way we collect data, let's focus on what's coming. Then later on, this comes up a lot when we talk about, oh, we want to digitize everything. It's like, we've got a bigger problem, but at least the new stuff is born. Okay, so we need money. We've got lots of data. We've got big storage needs. We want data to be accessible and shared. How do we convince governments to help fund this? We're the only ones that stay. Research. So you tell them, so, you know, you're wasting money. You're funding researchers to collect money, and they're not sharing it. So you fund another researcher to collect the same data over and over and over. This is a problem. They also lose because they funded the researcher to collect the data. Research retires, dies, moves on, forgets to take care of the data. We lose data all. And so you have to fund the recollection. In some cases, you can't do it. Astronomy, my old discipline, there is no such thing as going back into the data. The world has changed. It may have changed slowly, but it changed very, very quickly. You cannot go back and recreate observation a week ago, let alone 10 years. In some cases, that becomes really talk about nudging the asteroid. Occasionally people talk about, oh, there's an asteroid on a potential collision course with Earth. How do we know? We measure its position. And if you have observations from the last week, you have a pretty good idea where it's going to go. If you've got observations from 50 years ago, you can find it, then you've got a much better characterization, and then you'd have to decide whether to send those scores up. Anyway, the other thing that's come up a lot in a lot of disciplines is the ability to verify research. A lot of disciplines are facing this sort of we can't reproduce some results because we don't have. So there's a good argument for government to say, hey, so they also set requirements. They talk about national cultural heritage. They want to have input to policy. A lot of governments these days talk about evidence-based policy. They want it based on data. Where's that data? It's in the research community. Who can interpret the data? Research community. So they're looking to partner with researchers. And they also take care of things like reference materials for building atlases, catalogues, big aggregations. We have in Australia a project called the Atlas of Living Australia. Every single species ever recorded in Australia, native and also is referenced in that category. There are sighting records that go back 10, 100 years. There are photographs. There's all sorts of information stored. You can search this. You can include this in this. So making this stuff accessible. Now, of course, the government goes, okay, it's a great idea, but it's costs. It's expensive to do this. So saying, well, okay, that's true, but we're actually trying to do the work. So we can actually make this cheaper. We can get users to not take care of their data. Why should we teach every researcher how to do research data? That doesn't scale too well. It means a researcher spends time learning about stuff. So making life easier for them is important. You can scale the costs on the infrastructure and the services that everybody needs. So taking care of one file format for the research, taking care of astronomers, taking care of other. There's a lot of then the community builds their stuff up, project specific stuff. They provide their infrastructure, includes their skills. It's a small cost. The institutions can help support. That's slowly starting. And what you can say to them is basically there is a huge return on investment. Governments do the help researchers to do the work. It just takes a while. Now, researchers work in context. They have their problems and centers. Publishers nowadays want to see the data. Goes with a publication. The funders, they now talk about making the data available. So they want it. It's their part of their social contract. Researchers, unfortunately, have culture of their own. We did a survey 50 years ago where we looked at probably 100 different research groups, disciplines, and we found there were basically the 7 great themes. And I'll leave the slide later, but basically there are reasons when researchers say, I don't want to share my data. These are the reasons that come up again and again. Some researchers have all 7. They're really paranoid. Other people, they just have 1 or 2. You have to. So we went through a process, certainly in Australia, how we changed this. It's hard to change conversation. When Chai said, I can talk for 2 or 3 hours, this slide alone is probably the base. So, how do you build this new culture? So we're now in a world where many researchers, certainly in Australia and a lot of countries, understand about this, the benefits. One of the key ideas I will skip this point. I think I focus more on sharing of data rather than openness concept. There's levels of openness. There's an appropriate level. You're talking to somebody in astronomy, they understand open data from 60 years ago because they standardized file formats for sharing. You talk to a medical researcher, somebody who data, somebody who teaching data. They basically have much higher sensitivity to their data being paid too much. Where are we today in Australia? So we now have a national federation of research repositories with many tens of petabytes of storage. If you have research data in a certain discipline, almost certainly there's a place to take care of it. We have a national identity and access federation, so we have the ability to take most research in Australia. We have identifiers for researchers and for collections. So we have ORCID identifiers to identify who the researcher is, how they're connected to others, and identifiers for collections. It kind of sounds like a tech, which it is to start with, but it's actually also an incentive, because the things that researchers really value is two. One is money, the other one is publications. Suddenly data has much greater value. If the data is available, accessible, they get a benefit. Obviously, we have RNA networks. The disciplines have matured, so about different data formats. So every discipline has a set of metadata standards. Ideally, they have 1 or 2 standards. Some of them have 10 standards. We have national infrastructure. Really important funding policy. Nowadays, when you're funded by one of the 2 big research councils in Australia, there's a rule at the bottom that says you must share the data and explain why. Now, you can have a good explanation that says that it's sensitive. This, or you say, no, that's fine, I'll share the data, I'll put it in the if you fail to do next time you apply for a grant, you might not process. So there's a little bit of balance. Institutions are much more aware of their responsibilities. Institutions actually own the data. If you're the researcher who's collected the data, you kind of think you own the data. Institutions, they're your boss. Now, they may have particular approval processes to give you permission to do something. But at the end of the day, they're the ones obliged. They have the relationship. The other thing we have absolutely valuable is this. We have a research support workforce in Australia now. I've done a couple of surveys for Australian Research Data Commons the last 5-6 years. There's probably, in that category, there's probably around 6,000 to 7,000 people out of population. All right, how do we get there? Did we spend a lot of new money? No, we didn't. We took the money we were spent. What we basically developed was this horrible acronym, strategy, that said we've got 15 different funding programs out of 5 different ministries, and they give money for researchers to buy a microscope. But that only gets you a small amount of money. You only get like a scale. This strategy said was, we're going to give the microscopy community the same amount of money we've always been giving over a decade, but we're going to fund it once for the nation. We want the community to come up with a plan to take the investment and buy world-class microscopes, share, have a business model that's sustainable. They picked about 15 different disciplines, and they picked IT as the 16th space, this e-research industry. They basically said, you guys have to agree on everything. So in the e-research world, we talked about compute infrastructure, we talked about innovation environments, connectivity, networking, identity, and access management. Data was one of the major pillars of all of the disciplines, other groups that we had, astronomy, biosciences, geosciences, population health, all sorts of things. They had the same research infrastructure. So the e-research community in Australia was formed. We now have an acronym that goes at least with each one of those. Data one is now the Australian Research Data Commons. It's a framework, it's a practice framework around the sharing of data, helping to. And because there wasn't a lot of money to start with, the first thing it focused on perfectly was a focus on culture. First thing it did was it said, we can't afford to buy enough storage infrastructure for the entire nation, but we've got enough money to go around and teach people how to drive this conversation. All right. Is it just Australia? Well, kind of. We're the only ones who basically put together all of these funding. There are now similar models in other countries that have done parts of this, bring it all together. Australia did not play. Research is collaborative, crosses borders, it crosses institutions. So research is. Having a network is no point. It's only connecting to people. It's when you connect globally. So there's a whole bunch of different projects, organizations, that invest in this space like this. And standardizing practices, bring together people. Most of these groups are not about infrastructure. They're about leveraging. I'm going to stop there because Chai's starting to give me a signal that I'm already 15 minutes. But I'm happy to take questions.
Well, yes.
Yes. One of the incentives I can see donations. Stop. No, for example, if somebody and it's a business model, it is there. Are you going to stop it up?
So is this research data being used by business?
This is data used for business.
Oh, for business. No, because I mean the data it's well, it depends on the data itself. But in general, if you're using the data that research has collected for money, sorry, the rule is it's publicly funded to collect the data, publish it. Public if we use I don't know, genomic data to help companies, pretty kind of means it's probably there's lots and lots of nuances in general. Industry wants to get involved. They just have a partner. At the end of the day, it's collaborative research. Government, but absolutely, business. We have other programs. I was also going to mention too, one of the outcomes of Australian Research Data Conference, Research Data Australia. You Google for Research Data Australia, you'll see Research Data. It's a catalogue of all of these major repositories. I had a look at there just a moment ago. I did a search on all disciplines. There are about 16,000 data around. So references to where they're actually stored upon access to the data itself, but at least.
The bigger question is that it seems that there's also an explosion of data now and also in the future. And storage of the data is becoming a big problem. Who is going to be paying for the storage is also becoming a big problem. Of course, to some extent, it's domain related, but that means that you are using existing knowledge, right, to decide what data should be kept, data can be. But that goes again what you were saying, that maybe 20 years later you look back some usefulness in the data. So what's your perspective?
There's a few interesting angles to that. Firstly, who in general government. So this national infrastructure strategy was discovered. So when it was first devised in 2006, thereabouts, they said, we're going to try this for 5 years, see how it goes. And then they extended it to 10 years. After 10 years, they did a review. They said, another 5, we'll see how this works. We're going to make some changes. After that 15 period, they said, this is working. This is working. So it's now part of the company. So all of the other funding programs for research infrastructure, all that solid So we now know how much money, and it's indexed. So it's not a case of we're going to put $20 million or $50 million a year forever into the future. It's $150 million today. Next year it'll be 153, 105 million. So it's indexed. So there's that money flow. The other thing that's coming up is that institutions are investing in this because we're building these aggregating nodes. Most companies in Australia have one center that is taking care of data storage for the users. So they get co-investment that way. There's an interesting result that was found 10 years ago from one of our research organizations that said keeping data for 1 year costs X. Keeping data for 2 years does not cost 2x. That's like 1.5. If you actually extend it, plateaus, it takes about 3x to store the data. So what you do is you can actually plan ahead. Say, we're going to take everything. We're going to keep everything. Because storage densities are always going up. Performance. But basically, now have a business model or an understanding of the cost around research data storage. That's scale. There was a discussion, I think Gartner did talked about data. They talked about volume, speed, variability. And the variability was actually the most expensive. It's like, if you know how to keep genomic data, then keeping more genomic data is zero. It's just physical. But if you're keeping genomic data and strong data and something, it's complicated. So the cost is. So we're seeing a lot of these state-based nodes now starting to specialize to things that are very, very costly. We had a big discussion about how do we make decisions about what to do. The general feedback was nobody felt brave. There was nobody willing to put their hand up saying, yeah, I'm going to be on the committee that makes decisions. Nobody wants to. So they did. Now, not everything is flowing to these departments. So that's a different. Yeah, it's really good.
Cut it short. You well, we can discuss that tomorrow during the session that we have the open sharing. Yeah, we will talk a lot, and then tomorrow there will be some library stuff that we got funded for them. We try to open sharing point. So the next speaker, thank you, Marcus. Please welcome. I have to read that. Takafumi Nita from Muffin, and he will give a talk on the digital revolution for future agricultural research. And then he is the one who collecting the requirement from different users that are using the supercomputer at the Muffin. You know a lot of the requirement. So you have 30 minutes you can go over because of the time that just going slow is fine. Just don't worry, just keep your head. It's okay. Floor is yours.
Good afternoon. Hello, everyone. I would like to thank you for opportunity to give this presentation today. Let me introduce myself first. I'm not a researcher. I am in charge of supercomputers in the Information Systems Division of the Ministry of Agriculture, Forestry, and Fisheries in Japan. In terms of my background in system development, I have been primarily involved in the upstream processes of the waterfall model. I didn't start my career as a system engineer. I come from an administrative background. Hobby is karate. I hold black belt. My presentation is composed of the content shown here. First, services for agricultural researchers. Secondly, main features of the supercomputer SCS. We would like to introduce the small-scale supercomputer operated by our team. Thirdly, we introduce how SCS is being utilized by agricultural researchers. Lastly, describe SCS challenges and improvements. We provide various services to researchers at the Ministry of Agriculture, Forestry, and Fisheries in Japan. Mapping is a high-speed network service connecting research institutes and MAP. Internet connection is 20 gigabps. Mapping connection in Tsukuba City Research Institute is 10 gigabps. Mapping connection in the other areas research institute is 1 gigabps. We collaborate with Apan and AgWG. NSS, Network Service System. NSS operates services such as mail system, mailing list system, file sharing system that are available for MAP's research institutes. Users can prepare mailing lists freely and share wiki and files among members of the mailing list. NLS, Network Library System, operates Agropedia as well as a branch office of a National Diet Library. I am in charge of the scientific computing system. SCS offers supercomputer service and commercial application. This is the overview of the network system. We have mapping as the foundation of our system, which is a high-speed network. And the mapping network services like SCS, NLS, NSS are connected with a 10 to 20 gigabps network. Each system has a firewall to cope with the security issue within the LAN. This ensures for users comfortable and efficient services. Mapping has also been connected to APAN Wide Project, the Philippine Research, Education, and Government Information Networks, and SciNet. Next, I will explain about this part SCS. Let me explain the system overview of SCS. Starting from the user access route. Users need to connect to Mapping's network. Accessing mapping from the internet is done through VPN services. Logging in the login nodes can be done through SSH connections using public key authentication or via remote desktop using VNC Viewer. Access to compute nodes is routed through the login nodes. The connection between login nodes and compute nodes is established at 200 gigabps with infinity band. The compute nodes consist of 8 GPU nodes with NVIDIA A100 GPU, each with 4 GPUs. 2 general-purpose CPU nodes with 2 terabytes of large memory, and 54 nodes with 256 bytes of memory. Program execution and the compute nodes supports both batch-up execution and interactive execution. Storage is managed by DDN's object storage with a total capacity of 780 terabytes. File system is raster. The users can retrieve the licenses of commercial applications from the license server, and the applications can be allocated to the front-end compute nodes and the user's local machine. Ameda's data from the Japan Meteorological Agency and historical statistical data are available from the database. Users can access this data from compute nodes or their local machines. Main features of the supercomputer SCS. The current SCS has been in operation since March 2021. The total double precision theoretical performance of the SCS is 638 teraflops, with a total of 64 compute nodes. This is very compact supercomputer. Japan's largest supercomputer, Fugaku, has a performance value of 488 petaflops in normal mode. The performance ratio is approximately 1/760. SCS is operated on 4-year lease agreement. The total cost covering hardware, software licenses, system construction, and 4 years of operation and maintenance amount to 1.1 billion yen. Notable upgrades from the previous system include updated GPU nodes, a shift to full SSD storage, and change in the file system to raster. Commercial applications such as ANSYS, Gaussian, MOE, AgWG, etc. are provided to users. Special permissions for floating licenses for muffin-connected users are being obtained from software vendors. SCS has some advantageous points as shown here. One major advantage is the mixed configuration of GPU and CPU nodes, allowing for various applications. Additionally, efforts have been made to enable immediate usage when users need it. For instance, we can automatically set up a user's environment within a few minutes of receiving their application and enable them to log into the login node. Since the compute nodes uses a cooling careful heat management is necessary, but it is installed in a standard server room. It's estimated that introducing a water cooling system would cost 200 million yen just for facility construction. In the case of a small-scale supercomputer like ours, we prefer allocating those costs to compute nodes and services instead. In addition to providing computing resources and commercial applications, we offer the following services. Python training sessions. We conduct workshops covering the fundamentals of perceptron and neural networks to facilitate learning for deep learning. Our training sessions. Participants learn about data structures, basic programming, and progress to visualizing data through graphs. Additionally, advanced participants will also learn multivariate predictions and classification methods. Utilization of singularity containers. Generally, as logging and compute nodes don't grant users visibility. Installing open source software is restricted. With singularity containers, users can utilize open source software without requiring root access. For users who are unfamiliar with how to use Singularity containers, our service engineers to provide necessary support. As user support, we address various inquiries related to SCS as part of our attention your user support services. I will introduce some examples of how the computing nodes are utilized for research activities. Examples of GPU's node usage. In Jupyter Notebook, it's common to test running content related to Python available on the internet in activity. Testing large language models. We are testing with free LLM. I have also tested an interactive AI using the Japanese language model Ringa. Detection of standing trees for logging using a combination of game engine and deep learning. This study aims to identify target trees for logging. A virtual forest environment is created with a game engine, and the deep learning model is trained for identifying the target trees. Next, examples of CPU node usage. Operation of ocean data simulation system. This system focuses on the surrounding waters of Japan. This system simulates observational data into an ocean numerical model to produce the current and past states and variations in ocean conditions. Gene information analysis for rice variety development. This study conducts statistical analysis and genetic information sequencing to reveal useful genes. Simulation of forest damage due to snow accumulation. This study simulates the risk of forest damage based on snowpack data. Simulation runs for thousands of years and the data output reaches several terabytes. I will introduce some examples of how commercial applications are utilized for research activities. ANSYS is used. ANSYS is employed to simulate the temperature and CO2 concentration distribution within a greenhouse based on information gathered from various sensors. This analysis allows us to discover optimal arrangement and management practice for crops to grow under appropriate temperature and humidity conditions. Gaussian is used. Quantum mechanics calculations using Gaussian are applied to predict the behavior of electrons at the atomic and molecular levels of four components. Studying the electronic states of food components enables use to predict of their characteristics and potential uses. AgGIS is used. This study aims to create soil maps by combining various geographical data such as topography, vegetation, land use, and satellite images. AgGIS is used to visualize the characteristics and distribution of soils across Japan. Through surveys and interviews with researchers, we have noticed a wide range of usage by various users. While many programs can be executed using GPU, Now, traditional CPU nodes are still heavily utilized. The amount of data being handled, both for input and output, has been increasing. Researchers express a desire to use GPUs and compute nodes not only for calculations, but also for visualizing 2D and 3D data. This includes visualization applications such as ANSYS, MOE, and Field View. Current regions applications are run on local workstations, but there are limitations such as availability only within the laboratory or during off period. The power consumption of supercomputers is also a significant concern. Supercomputers, including related facilities, demand a substantial amount of electricity, leading to high electricity costs. Since researchers are not necessarily programmers, the number of users effectively utilizing computing resources is quite low. Researchers who use supercomputer for the first time may have troubles in learning how to use, and finally they may give up. So we need the environment that users can make consultation easily. It seems is a time-consuming task for beginners to set up a local environment. Access to login node involves CLI and public key authentication. Some users find their processes cumbersome, along with the installation of SSH clients. The next slide towards our discussion to cope with this issue. We are working on resolving the challenges mentioned on the previous slide and aiming to create a supercomputer accessible to everyone. In the next system, from 2025, we are considering the following. As for the compute nodes, we aim for a balanced performance ratio between GPU and CPU nodes based on user utilization rate. Since some programs run on single core, we also want to ensure a proper clock speed for each CPU. While the latest CPUs tend to have more cores and lower clock speeds to reduce power consumption, we recognize the need for careful CPU resection at SCX. Considering the cost of using all SSD, we are seeking for a hybrid configuration of SSD and SAS for data capacity. While data processing speed is a concern, the ability to store big data is crucial. Considering the budget restriction, the proper balance between processing speed and data storage is an outstanding issue. We are thinking of introducing NICE DCV. NICE DCV offers high performance remote access to 2D and 3D software applications, compatible with both Linux and Windows. We see it as a way to further use the GPU and the compute nodes. To reduce power consumption, we plan to incorporate monitoring function for the power usage of the supercomputer system. We can limit power consumption during periods of low utilization to reduce total power consumption. In creating an environment accessible to everyone. We are planning to use GitLab to establish a platform for program sharing and communication. In order to expand the scope of utilization, we intend to publicly share program code and enable user-to-user messaging. I will briefly introduce Open On Demand in the next slide. Open On Demand is a user-friendly tool that allows you to access compute nodes using a web browser. It also supports web authentication, including multi-factor authentication. From the web, users can perform job management, file operations, application execution, and run visualization tools. When it comes to running applications, you have access to multiple applications and tools. For example, you can run visualization software and numerical simulation tools. The platform also provides tools for visualizing job output and data, making data analysis and result visualization easily. This is why we plan to introduce this tool to FTA. In conclusion, by understanding the user's needs, we are trying to deploy the most efficient supercomputer services with minimal investment. That concludes my presentation. Thank you for your attention.
Excellent presentation. Thank you very much. You keep your pace and then not spending time over. So that's very good. So any question for Anita-san? Yes, that's all like that. Thank you very much one more round. Okay. Thank you. We will not have the after session, the open syllabus. So we go up to the after lunch, go up to the 6th floor. Started around 1:30. And then, after that, we come back to one more session. But we have the session, and then there's about NASA, and then I asked Captain Bruno to give his take on the nuclear rescue, forest fire fighting. On that. And then when we have time left, I will show further about the informatics that we forest fire, fire, hydrology, slides in sketch already. You can follow it. Just a link and then explain what they are. Interesting is the talk, but from NASA plant, but they cannot be here because the Diane David, she has a surgery. So I asked her to stay. Enjoy your lunch and come back after. Thank you very much.